Okay, hello everyone. Uh, Today we are going to cover the practice assignments of week 9 and week 10. Let's start off with week 9. Okay, we are starting off with the practice assignment of week 9. Okay, so this is the first question. Okay, yeah. So we are given this corpus. Okay, this is given to us. What is the size of the vocabulary of the above corpus? Right. So vocabulary consists of all unique words from the given corpus, right? So, is it here? Okay, so yeah, it's pretty straightforward, but I'm just covering it for the sake of completeness. So we are going to take each word, right? And so it's not given that we have to skip stop words, which we generally do. But since it's not given, we'll take all of them. So I'm just noting down all the unique words that I'm coming across. Okay, computer is there. System, I'll add. Response is new, and then time is new, then user is already there, then interface is already there, management is new, system is there, system is there, engineering is new, for is there, improved is new, response is there, time is there. So I guess it's done, right? 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15. So 15 unique words are there. So this should be the correct answer. Okay, so we can imagine how huge the vocabulary is. We can imagine for a real world data set, for example, Wikipedia, right? So we can imagine the how large the vocabulary in NLP task is, right? Okay, next question. Let count WC be the number of times the words W and C appear together, and count W and count C are the number of times the words W and C appear in the corpus respectively. N is the total number of words in the corpus. Then PMI is given by what formula, right? So what is PMI? PMI is point-wise mutual information. It has this formula, log of, in the numerator, we have probability of W, C. And in the denominator, we have probability of W multiplied by probability of C. And this probability can be written as a fraction, right? Which is equal to count where W and C come together divided by the total number of words in the vocabulary, and probability of W divided by, sorry, count, we are expanding PW, right? So that will be count of the how many times W comes divided by N, and this will be count C divided by N, right? So that's what we get, and that will be equal to N goes up, so it comes out to be count WC multiplied by N divided by count W count C. So this should be the alternate form of the formula. This formula on any of these you can use since we are given count, so this should be the correct formula, which is C, right? Yeah. Okay. That's the correct answer. Next one. In order to compute SVD, the matrix has to be a square matrix. The statement is false, right? Because SVD, it's not necessary that for SVD, the given matrix is square. You can calculate, you can compute SVD of a rectangular matrix as well, right? So let's say X is a rectangular matrix. Then it gives a decomposition, singular value decomposition, right? It gives a decomposition in the form of three new matrices, U, sigma, V transpose. Let's call them these U, sigma, and V transpose. This multiplication is equal to X. So from X, we are getting 1, 2, 3 matrices, which is based on the eigenvalue decomposition. And it is not necessary for this decomposition that X should be a square matrix. It can be square, but rectangular also works. So let's say X is your M cross N rectangular matrix, right? And what will be the dimensions of U? U will be your M cross M matrix, and V transpose will be your N cross N matrix, and sigma will be your M cross N matrix. So these are going to be the dimensions of different matrices. And as you can see, it's not a square matrix. So the answer is false. Okay, next one. Let X be the co-occurrence matrix such that ijth entry of X captures a PMI. So it's basically a PMI matrix, as you can see, right? Each row of X corresponds to the representation of the ith word. Okay, each row corresponds to the ith word's representation. Okay, suppose each row of X is normalized, which means divided by the L2 norm of that row. Then ijth entry of X transpose captures what? Let's see. Okay, so what is X? X is basically the PMI matrix. Well, that doesn't matter. It could be co-occurrence, simple co-occurrence matrix, or it could be a PMI matrix. What we are given is each row of X is a representation of the ith word. That's what we are given, right? What else? We are normalizing each row of X. Suppose each row of X is normalized, right? What does that mean? Which means, let's call it X naught. Firstly, if let's say, a vector is given and you have to find the normalized form of that vector, you will divide each value in that vector by the L2 norm, right? Which is the length of that vector, right? That's what you'll do. So let's say X is this. Let me call them X1, X2, X3. Let's say this is your X vector. We'll call it X vector. And let's say the second row is Y1, Y2, Y3. I'm just giving them some names so that we can understand what we will get after getting X transpose. Yeah. Okay. So we are normalizing each row, which means X1 will be divided by mod of X, X2 will be divided by mod of X, X3 will be divided by mod of X. Mod of X is the length of this vector, X, right? Similarly, what will we get for the second row? Y1 will be divided by mod of Y, Y2 will be divided by mod Y, and so on. So let's take these two rows as an example. What is it that we'll get as X transpose? Let's see that. So this is, I'm not writing the mods right now. We will consider them. So X transpose is going to be like this, right? More things here and more things here. So this is what we are going to get as X transpose. The division by mods I've not done. We'll do that. Okay. Now let's say, so there'll be some elements here, right? Let's take this element. What will be this element? I'm just arbitrarily taking some element. What will be this element of this matrix X transpose? Let's see. What is going to be this element? That's what we are going to see. So this multiplied by this is going to be the first element, and this row multiplied by this vector is going to be this element, right? So what would that be? X1, Y1. X1, they are normalized, right? So X1 divided by mod X is there, Y1 divided by mod Y is there, plus X2 divided by mod X, Y2 divided by mod Y, plus X3 divided by mod X, Y3 divided by mod Y. This is going to be this element, right? And what that comes out to be, you can just simply write it like this, right? Divided by mod X, mod Y. And this is basically the dot product X dot Y divided by mod X mod Y. And this is your cosine similarity between x and y, right? And what are x and y? Basically, x, as per the question, this is the ith row, and this is the jth row, let's say. Then this comes out to be the cosine similarity between the word I and word j, right? So eventually it comes out to be the cosine similarity only. This should be the correct answer. Okay. Next question. Let the co-occurrence matrix X be this M cross N matrix. Once we do a K rank approximation, we take W word to be U sigma, right? What are the dimensions of W word, right? So we actually did this. Let me write the answer here only. This was our SVD, right? And we know this is M cross M. Well, if we take the K rank approximation, then how do things change? When we take a rank approximation of x, then x actually remains m cross n. However, we'll take only the m rows and k columns, right? So this becomes m cross k. For a k rank approximation of x, we're going to take not m cross n, we're going to take m rows and k columns, so that becomes m cross k. And then sigma, from sigma, we'll take top k singular values, and then v transpose, we're going to take k rows, so it becomes k cross n. So these are going to be the dimensions. What are they asking? W word is u sigma. What are the dimensions of W word? So u sigma is going to be this, and the dimensions are going to be m cross k. Okay. So no, m cross k. This is going to be the correct answer. Okay. Next question. At the input layer of CBOW model, we multiply a one hot vector x dimension v with the parameter matrix W, which was W context, right? Dimensions k cross v, right? K is the embedding dimension, and v is it should be capital V actually, same as this one. P is the size of vocabulary, right? What does each column of W correspond to, right? Let's see. Each column of W, right? So let's quickly see how CBOW looks like. Let's say this is our input, right? Input, so in CBOW, what is the input? The input is context and the output is word, target word, right? So this is a context. Any questions there? Are you typing anything? No, right? Okay. Yeah, so this is a context which we input. Let's say its dimensions are, yeah, this will be V only, right? Vocabulary size. It will be one hot vector. And then we have an embedding dimension, embedding layer. Let's say that is H, that gives us H, and the dimensions of that will be K, right? And then in the output layer, we would have, I'm calling it W hat, let's say, and its dimensions will be again V, right? Size of vocabulary. Here we are going to have the context matrix, W context, and this will be K cross V. K cross V. And here we are going to have word matrix, and that is going to be V cross K. I think in the slides and in the recordings, this is K cross V. This should be V cross K. Okay, consistent with what we've been following right from the beginning, first week. This is what this convention we are following. Okay, what was the question? One hot vector. The C is a one hot vector. Okay, they're calling it X, but yeah, let's call it C. What does each column of W correspond to? W is their parameter matrix with which we multiply one hot vector. So basically, they're talking about W context. Okay, they're talking about this matrix. And your H is going to be a multiplication of W context and C, right? Your W context is K cross V, and then C is V, so this comes out to be K, right? So everything fine. So what they're asking is, what does W context contain? That's what they're asking, right? And C is a one hot vector. Let's say C is some vector like, something like this. Right? This is one hot vector. And so what? How would H be like? What would H be when you multiply W context with C? Let's say W context is some matrix 1, 2, 3, 4, 5. Some matrix is W context. You multiply this by a one hot vector. So what will happen, right? You multiply this with this, right? What do you get? You only get this element, right? You get that element here, and then you multiply this row with this column once again. Again, only you will only get this element, and so on. You multiply this with this, you only get this element because the things become 0. So eventually, you can see that when the second element in the one hot vector is on, then you get the second vector here, and so on. So second element is on, you get the second vector. And you can take more examples. When in general, ith element is on in the one hot vector, then you get the ith column. Yeah, ith column from W context, right? You see that? So which means when you feed this, right? When you feed any one hot vector for any context, then only one vector in W context gets affected, right? So, and as H, you only get that vector. And that eventually becomes the representation of that word, this word, second word here. In general, ith column of W context becomes the representation of the ith word, which is fed as a context. Okay. What are they asking? What does each column of W correspond to? Each column of W corresponds to the representation of the ith word in the vocabulary. So this should be the correct answer. But just one small thing I'll add. The representation of the ith word when used as a context. Okay. See, we are feeding context words and we are getting target words, right? We're actually getting two representations. One representation is in W context, another representation is in W word. Both these matrices have the representations. So the thing is, when the word is used as a context, then probably you can use W context. But in order to get the embeddings or the word vector representations for the words, we should better use W word. We should better use the columns of W word. Okay. Maybe I can clear this with an example. If this is not, if you don't understand this already, maybe I can take an example maybe in a while, because probably the next question is a little connected to what I'm saying. Let me finish the 7th question and then I'll talk about what I'm talking about. Okay. Yeah. So to sum up, to finish this question, the W context matrix contains the representation of the ith word in the vocabulary when used as a context. That's what I'm saying, and I'll explain this in a while. Okay. Okay. Next question. Consider the word W and context C, which appears before it. For example, W could be the word barks and C could be the word dog. VW. So let's be clear with the conventions, right? VW is what we call a vector of word W. UC is what we call a vector of context C. Okay. These are the representation of W and C. Assume that you're training the CVAO model. You should write continuous bag of words, because bag of words, we know it's very different. Right? It simply contains the number of occurrences. CVAO contains the learned representations. Using n is equal to 1, fine. Let y hat be the output of the model. Y hat is the probability distribution over all the words in the vocabulary. Okay. In particular, YW hat is the probability assigned by the model to the word W, right? If you're using gradient descent to train the model, eta is the learning rate, and the update rule for VW is given by this. Okay. Yep. So this question is about gradient descent, right? So gradient descent applied on VW. Right? So there are so many parameters in the model. We are currently talking about gradient descent being applied to the vector VW, which is the vector representation of the word W. Same as before, as always, VW is equal to VW minus eta gradient of loss with respect to VW. This formula will be the same as we've been using. Now, what we need is this gradient of loss with respect to VW, right? What is the loss? The loss is that softmax, right? And in the lecture, there is a derivation for that. I will not get in the derivation because it's already very clearly explained there. So that this gradient of loss with respect to VW comes out to be minus UC 1 minus YW hat. This derivation I am just taking from the slides. If you want, you can see the derivation is very straightforward. What is UC? UC is the vector representation of the context C. YW hat is the value, the probability value that we are getting for the word W in the output vector Y hat, right? Let's try to understand this. Okay, let me finish this question's answer, and then we can talk more on this. So this we got, right, and we can put it inside this, and we will get VW is equal to VW minus plus eta UC 1 minus YW hat, right? This is what we are getting. VW, so there's a plus here, and then UC is a plus here, and then here we have YW hat. So this A should be the correct answer. Okay, this is the correct answer. Now, if you see this, right, let's try to understand in which cases VW will be updated, in which cases VW will not be updated. Let's take some extreme cases. Let's say YW hat is equal to 1, which means already the model is giving us the probability 1 for the target word W, which is the ideal situation. Whatever word had to be output by the model is already predicting that as the word, which means YW hat is equal to 1 and rest of the values in Y hat are 0. That's the ideal situation. So in that case, what will happen? This is 1, so this becomes 0. VW is equal to VW, which means no update is made to VW. That is one case, correct? Case when case 1, when YW hat is equal to 1. Let's talk about another case. Let's say, as an extreme case, YW hat is given to be 0, right? When this is 0, then what does it come out to be? VW is equal to VW plus eta UC, right? That's all. Yeah. YW hat becomes 0. So this is what we get. Now let's stare at this. So when YW is equal to 0 or any value less than 1, right? Then what are we doing? We are adding a fraction. Some fraction we'll get from here. We are adding a fraction of UC to VW. What is VW? VW is a vector representation of word W. What is UC? UC is the vector representation of the context C. When VW is not what we want, we are adding a fraction of the context words representation to VW. And when we do that, what happens? You might know it from perceptron, right? Y is equal to something, Y is equal to Y plus X. That kind of rule was there, right? So in that case, we were bringing these two together, right? In perceptron, if you remember from the first week, a similar thing is happening here. So when we add in each iteration, right? In each iteration gradient descent, we are gradually bringing UC and VW together. We are bringing VW and UC together eventually so that the cosine similarity increases, right? Cosine distance reduces. We are trying to bring them together. We are trying to bring the word and the context together. Note this. We are trying to bring the word and the context together, right? What is the result of doing this? Let's take an example. So let's take this example. Let's say the word is dog, and the context is, let's say, sleeps. Okay. So VW is a vector of dog. Oh, okay, no, not like. Let's take two examples. Word is dog, context is sleeps. Another uh, example, let's say the word is cat and the context is again sleeps. Okay. This is what we're given. So when we keep applying a rule like this, then eventually what happens, the vector V of dog becomes closer to vector U of sleeps, and the vector V of cat comes closer to vector U of sleeps. When this happens, then eventually, so when you're trying to bring this closer to this, you're trying to bring this closer to this, and the result of this is that eventually V dog and V cat come closer. And that is why the similarity between V dog and V cat increases. Right? That's how the contextual information comes in, right? However, a side thing that is happening for making this happen is the following. We are bringing dog closer to sleeps. We're bringing cat closer to vector representation of sleeps. The U representation, please note, not V representation. Right? So V dog is closer to U sleeps and V cat is closer to U sleeps. Right? We want dog and cat to be closer to each other, which is happening in the matrix V. We don't want we don't want dog and sleeps to be together. Dog and sleeps are coming out to be together when you look at U is in W context, and this information is in W word. So this means that W word matrix consists of the correct representations for the words. However, the matrix W context consists of the representation of words when they are to be used for context. For some probably special purposes, you might want to use these representations. However, for any downstream task like, sentiment analysis or anything that you want to do in NLP, you want to get the word vectors for words, you should use W word. Is this clear? By the way, in the matrix W word, there'll be a representation for V sleeps, and that will be the correct representation. You getting this? That will be the correct representation of sleeps, where V dog may not be very close to V sleeps and V cat may not be very close to V sleeps. Right? Did I make myself clear? I'm not hearing anything. So, Nitin, how many people are there? Okay. Okay, one moment. Let me stop share.
Sorry, Naka, I mistakenly left this meeting. Yeah, so
No problem. One moment. So yeah, so where are the participants? This is just now left, is it?
not just now. I mean, when you were on the seventh was last question, then they left.
Okay, okay. 1 minute. Shall I stop streaming, Nitin?
Yeah, then stop stream.
Okay, I'll stop share also.